here. We made it. Yep, there's a robot dog right next to me. Why? I don't know. It felt cool. So I thought I'd add it to today. Why is there sort of an odd delay? I don't like that. Alright. So yeah. It's a Saturday and we left off yesterday with the pre-training using the trainer API on the HuggingFace side, and on the Carnegie Mellon University side we're talking about language modeling. LM, language model evaluation. That's where we were. There we go. My brain was not braining just for a minute. Yeah. So, I do want to start here because I want to start here. Yeah, no, I don't know why. I just feel like I want to start here. I continuously feel bad when it looks like the dog is feeling bad. See, right at this moment, and then he becomes happy, and then he becomes musical. I'm okay, don't be sad. And then he's sad. I keep saying he because there was a pink version, but I felt like my style works with the blue version. Alright. Are we too big? Should they be smaller? So that you can see the background as well. Alright. So, this lesson is supposed to be training without the trainer API, I think. Just using PyTorch. So this video might be long, I don't know. Let's see. But the idea is we'll see how to achieve the same result as we did in the last section, but without using the trainer class. We assume you've done data processing in section 2. Here's a short summary covering everything we need, which is the data processing part, containing the data set, the tokenizer, the mapping, and the padding. All right. Whoa, the whooshes are really, really, really loud. That's not cool of them.
Write your own training loop in PyTorch. In this video, we'll look at how we can do the same fine-tuning as in the trainer video, but without relying on that class. This way, you'll be able to easily customize each step of the training loop to your needs. This is also very useful to manually debug something that went wrong with the trainer API. Before we dive into the code, here is a sketch of a training loop. We take a batch of training data and feed it to the model. With the labels, we can get computer loss. That number is not useful on its own, but is used to compute the gradients of our model weights.
Is it too loud?
That is, the derivative of the loss with respect to each model weight. Those gradients are then used by the optimizer to update the model weights and make them a little bit better. We then repeat the process with a new batch of training data. If any of this isn't clear, don't hesitate to take a refresher on your favorite deep learning course. We'll use the Glue MRPC dataset here again, and we've seen how to preprocess the data using the datasets library with dynamic padding. Check out the videos linked below if you haven't seen them already.
Oh, removing the columns, and renaming label with labels. Those two are lines added extra that we don't see here. I thought it's the full code, but it's not. And I did try to fix the sound because the video is super like way louder than me. It goes up to the red part, so I tried to adjust that.
With this done, we only have to define PyTorch data loaders, which will be responsible to convert the elements of our dataset into batches. We use our data collator for padding as the collate function and shuffle the training set to make sure we don't go over the samples in the same order at each epoch.
So data loading is used to train data loader, evaluation data loader. Did we use that last time? Having a hard time remembering that because after the already training. This I remember the arguments, but we didn't do batching. Okay, my brain is working apparently. Okay, I guess that helps with what do you think? That helps with making it faster.
To check that everything works as intended, we try to grab a batch of data and inspect it. Like our dataset elements, it's a dictionary, but this time the values are not a single list of integers, but a tensor of shared batch size by sequence length.
Okay.
The next step is to send the training data in our model. For that, we'll need to actually create our model. As seen in the model API video, we use the fromPretrained method and adjust the number of labels to the number of classes we have on this dataset.
Okay.
Here, 2. Again, to be sure everything is going well, we pass the batch we grabbed to our model and check there is no error. If the labels
just looking at it, okay.
are provided, the models of the transformers library always return the loss directly. We'll be able to do loss.backward to compute all the gradients, and we'll then need an optimizer to do the training step. We use the AdamW optimizer here, which is a variant of Adam with proper weight decay, but you can pick any PyTorch optimizer you like. Using the previous loss and computing the gradients with loss.backward, we check that we can do the optimizer step without any error. Don't forget to zero your gradient afterwards, or at the next step, they'll get added to the gradients you computed. We could already write our training loop, but we'll add 2 more things to make it as good as it can be.
Okay.
The first one is a learning rate scheduler to progressively decay our learning rate to 0. The getScheduler function from the transformers library is just a convenience function to easily build such a scheduler. You can again use any PyTorch learning rate scheduler instead. Finally, if we want our training to take a couple of minutes instead of a few hours, we'll need to use a GPU.
I've had no luck with that. I don't know why. I always mess up and make it crash. So I'm hoping this helps.
The first step is to get one, for instance by using a Colab notebook. Then you need to actually send your model and training data on it by using a Torch device. Double check the following lines point a CUDA device for you, or be prepared for your training to last more than an hour. We can now put everything together. First, we put our model in training mode, which will activate the training behavior for some layers, like dropout. Then we go through the number of epochs we picked and all the data in our training data loader. Then we go through all the steps we've seen already. Send the data to the GPU, compute the model outputs, and in particular, the loss. Use the loss to compute gradients, then make a training step with the optimizer. Update the learning rate in our scheduler for the next iteration, and zero the gradients of the optimizer. Once this is finished, we can evaluate our model very easily with a metric from the datasets library. First, we put our model in evaluation mode to deactivate layers like dropout, then go through all the data in the evaluation data loader. As we've seen in the trainer video, the model outputs logits, and we need to apply the argmax function to convert them into predictions. The metric object then has an...
I think another time we did softmax, and I don't know the difference.
That batch method we can use to send it those intermediate predictions. Once the evaluation loop is finished, We just have to call the compute method to get our final results. Congratulations! You have now fine-tuned the model all by yourself.
Not really, but I will. I do want to search about PyTorch, argmax. Is there a versus? Mango softmax. Anything max. Just maximize the learning, I guess. I don't know. I mean, I should know, but I don't know. Okay, let's just look at argmax first and then softmax next and make our conclusions by ourselves. Okay. So argmax returns indices of maximum value of all elements in the input tensor. Softmax applies softmax function to the nth dimensional input tensor, rescales them so that the elements of the nth dimensional output tensor lie in the range of 0 and 1. Sum up to 1, really? Oh, so softmax is for percentages. That makes a lot of sense. Okay. Just the idea is to be in the range of 0 to 1, whereas argmax maximizes the stuff. Do you know what that means? Yeah? Oh, you're worried. Me too. At least I know why we use softmax now. Okay. So, to go over everything we went over, I can continue with this, but just like give myself second part and not run what we ran. Yeah, you're already here, so I'm just gonna add one, say the title of this part. Not you there. And then start. Do we want to do the remove columns thing? Because it was before padding. We did hold up. Right here.
And we've seen how to propose has.
Okay, so it was this. Equals you yourself dot remove. Come on. Why are you column? Is there an S? Yes. And then the column names are hello. What ML course are we taking? There is a course on I'm gonna share it, that's why I'm being slow, so that I can put it in the chat, on HuggingFace, called the HuggingFace NLP course, and it's on huggingface.co/learn. They have many other courses, by the way. So this is the one that I'm currently taking, but that's not the only course I'm taking. I'm also taking this Carnegie Mellon University's Advanced NLP just video looking at the videos. This one is more practical, the other one is obviously more theoretical. It's because it's from university, but yeah. Oh hey, Sleepy Yuki's here. Hi, Sleepy Yuki. What's up? Oh, did I learn about sparse, PCA, and other terms in ML that have the word sparse in it when you look at the index? I'm not sure what you mean, Mr. Mango. Preparing for bed. Things are going pretty well. Lovely Saturday. Yeah. I think. Yeah, pretty good. I did see the notification of you going live yesterday when I was also sleeping, so it's really fun just catching each other that last minute of the day. I hope you have the loveliest dreams, the most relaxing sleep you've ever slept. And please do go to sleep, because it's good for our body and for our brain. Yep, we are fragile. Time zones. It's fun though. They suck, but they're also fun. Because, like, when you first learn about them, you're like, are they even real? Wait, people don't live the same way? Wait, seasons are different? What? Sentence 1, sentence 2, and IDX. Okay. We are removing sentence 1, sentence 2. I only watched StatQuest ML videos before learning about these things, so I really don't know what people learn from a machine learning course. Fair. It seems to be in the index machine learning books. In indexes, alright. But the people I asked who is getting a degree in DS say they don't know what these by the terms. So maybe sometimes they're just used differently in different places. So maybe it's that, but I don't even know what you mean by a PCA. Maybe I recognize it if I Google it. I don't know. Let's try. Sparse principal component analysis, a technique used in statistical analysis and in particular the analysis of multivariate datasets. So it's more math. Okay, fair. The goal is to obtain a small number of principal components, each being a linear combination of a subset of the original variable. Seems interesting. And like, seems really cool, but okay. I'm not that well versed in machine learning, so I can't answer you, but I do think that it might be talked about somewhere in this one. You can, I suggest you go to their website and look at the lectures slides and see if it's something that is going to be discussed. And the slides are here. And I don't know which like where it would be. Is it a part of the training? Is it a part of the evaluation? So if you know that, then you'll have a easier time searching for it. Looks like it's a part of the training. Okay. So did I remove IDX as well? I did not, and I meant to remove IDX. And then second part is I do copy things and then I make mistakes, so do bear with me. we update the word labels. It's rename column without an S, name column, and then label becomes labels. Right? Right. Cool. Even though you didn't do that, I don't know if I'm making a mistake or not by doing that. Let's see. All right, you do that. So preparing for training. Before actually writing our training loop, we will need to define a few objects. The first ones are the data loaders we will use to iterate over batches. Oh, that's why we were using data loaders to do the loop thing. Okay. But before we can define those data loaders, we need to apply a bit of post-processing to our tokenized. I just did that. Hey. The remove and the rename. Okay. To take care of some things that the trainer did for us automatically. So we need to remove the columns corresponding to the values that the model does not expect. Oh hey, I don't know about PCA, but K-sparse neural nets are cool. You can keep only the 10 strongest neurons turned on and turn off all other labels. You introduce that gradually during training and continue to do that after training. It can make it much easier to understand as a human. That's really, really cool. Seeing which neurons turn on under which circumstances. Oh, force turn off all neurons. Where was that? Okay. And force. Okay. Other labels. Whoa. Being sleepy and being able to understand, answer a question. Whoa. I should, clap. Clap. Thank you for that. Okay. That was K-sparse neural nets. So it's like choosing things that's really cool. It learns to represent things as a combination of just a tiny handful of active neurons. Okay, so you yeah. And you turn off the others. It's not like you're just looking at them. You actually turn them off. Wow. Thank you. That was really cool. I don't think I've come across them. Okay, I forgot to do that part, which is set the format of the data sets so that they return PyTorch tensors. Sensors. Yeah. So, oh hey, all right, I'll do that. Fine. It's just that okay, I'll just do it as a different code because I guess it doesn't matter if the padding happens before or after, but it does matter that I need to install those things, and then I'll probably need to install this and then do the restart, all of that again. Do I need to? Okay, there we go. Okay, you do that, and then this part. Oh, we're just looking at it. Okay, I was like, why are we just calling this? To just check, to see the columns that we have. All right. And then we define our data loader, and the idea is that so it can iterate in batches of 8 through our data. Okay. So you are running. Not there yet. Okay. So we have two data loaders, one for training, one for evaluation. And we give it as a function our training data set and our validation data set. So yep, you're still running. Okay. And we're just looking at what's inside by saying for batch in the data loader, so just the first one, looking at the shape, and then batch item, looking at the shape. Oh wow, okay. Alright, you did that. I'm gonna try running this one more time and see if I get an error or if I need to restart. Okay. You're running. That's good. Basically truncating is a main part of most things sparse. Just maybe like making a subset, making it smaller and more humanly understandable. And I'm just saying that I'm without any authority. Oh, I forgot to bring. I'm just looking at what's inside the training set right here. So now, what did I do? In the remove, man. I should put it right. Sorry. Okay. Is it the same for the rename? Then what did I do? Remove columns. What did I do? I'm just gonna copy this. Allow me to just write something in my... Oh! They're literally the same. The only thing is that there are spaces. A space here and a space there. That's it. So why are you giving me an error? Error sentence 1. Why? Did we already remove it? Hold up. I'm gonna comment you guys out and see if we, or actually don't need to comment you guys out and see if we already removed you. No, it's there. What? I don't understand what's going on here. We have tokenized data sets, don't we? The fact that it just makes me feel like, okay, fine, copy paste everything and then run it. And it worked. I don't know what was different. Now I have to check. Oh, I found it. Oh, whoops. This was wrong. Label to... Did I just spell it wrong? This is fun, isn't it? Let me see what did I do wrong? Nothing! Again, it's just a space, for God's sake. No, wait, that's the issue. And if I do it one more time, you'd probably give me an error. Because it doesn't exist anymore. Sorry about that. Okay. Thank you. So yeah, we saw these. Still don't know what was wrong with the code that I wrote with my hands. It just makes me feel more inadequate. And just like, fine, I'll copy paste everything if that's all you need. So the data loader, we're giving it our training set, our validation set tokenized, and also our data collator. So let's paste that here, run it, and this part is just looking at one line of the data loader. So we're looking at one item. It has labels with a torch size of 8, input IDs, token type IDs, which is something we actually need, and the attention mask. That's pretty cool. That's really cool. So note that the actual shapes will probably be slightly different. It was, yeah, since we set shuffle to true for the training data loader, and we are padding to the maximum length for each batch. Yes, that's true. Yeah. So we have a data collator that we didn't really apply, but we are applying it here. And the padding happens for batches of 8. Got it. Now that we're completely finished with data processing, a satisfying yet elusive goal for any ML practitioner, let's turn to the model. We instantiate it exactly as we did in the previous section. So we're just calling our model. And I think our model was BERT encased. Yes, BERT base uncased. All right. So we're calling it here. We're saying we need to. Oh, okay, it's fine. I'll do that later. Okay. So yeah, to make sure that everything will go smoothly during training, we pass our batch to the model. The batch is, wait, how come we're calling it batch? Where are we? We are not, like, I know batch is for each batch in the data loader, but does batch become its own thing now? Can I call it? That would be weird. Like, does it become a variable outside this scope? Is it 4? 8 by 2. So it's a batch. Whoa. All HuggingFace transformer models will return the loss when labels are provided. And we also get logits, 2 for each input of our batch. So the tensor size is 8 by 2. Okay. We're looking at the loss, which is this number, and then we're looking at the logit shape, which is that. We're almost ready to write our training loop. We're just missing 2 things, an optimizer and a learning rate scheduler. Okay. Since we are trying to replicate what the trainer was doing by hand, we will use the same default. The optimizer used by the trainer is Atom W, okay, which is the same as Atom, but with a twist for weight decay regularization. That's a paper. I'm not gonna open a paper. Just tell me what's weight decay regularization. A form of regularization that penalizes large weights in the network. Okay. It does this by adding a term to the loss function that is proportional to the sum of the squared weights. This term reduces the magnitude of the weights and prevents them from growing too large. That is very interesting. Thank you. This is from 2019. This here. All right. So atom W is atom with weight decay. Got it. And we're calling it. Now we have an optimizer. There's a warning. Oh, deprecated. Whoops. Ah. So it's not inside. Alright. Will be removed in future versions. Alright. Oh, we are giving it a learning rate. Why? Finally, the learning rate scheduler used by default. It's by default. Okay, it's just linear decay from maximum value to 0. To properly define it, we need to know the number of training steps we will take. Didn't we take like 1,300 something last time? Or do we mean steps or epochs? Epochs were 3, and we were printing output every 500, I think. Yeah. Which is the number of epochs. Oh, so by steps you mean epochs. Okay. We want to run multiplied by the number of training batches. Which is the length of the our training data loader. How much was that? Trainer uses 3 epochs by default, so we will do the same. All right. See, it was 1,300 something. So we are getting a scheduler. All right. We're saying we want 3 epochs. Number of training steps becomes the number of epochs times the length of our data loader. And then we're just printing that, which becomes this number. For the learning rate scheduler, we're using this getScheduler method from transformers, and we're asking for a linear. Let me see. So in getScheduler, come on, you can do this. Load it. There we go. So we have the type, and then optimizer, and then number of warm-up steps, number of training steps. Okay, so we give it the number of training steps after we calculate it, and then we have our scheduler. Okay. Now for the training loop. One last thing, we will want to use the GPU if we have access to one. On a CPU, it might take several hours. To do this, we define. Oh yeah, we'll just check if we're using CUDA, and then okay, we're saying if CUDA is available, make the device CUDA. Okay, otherwise it should be CPU. We're now ready to train. To get some sense of when training will be finished, we add تقدم, the thing. Where did I see that? I saw it somewhere else, and they told me that it means, تقدم means like forward in Arabic, and then I think it meant something in Spanish. It was like love or something. It was really cheesy and cute. We're now ready to train. To get some sense of when training will be finished, we add a progress bar over our number of training steps. Yes, using the تقدم library. It was in code written by our professor. First lecture. Look at that, things being neatly tied together. So we are making a progress bar over the number of training steps. And where do we put it? At the end. Okay. And it will look really pretty. That's it? That's the training? Okay. Is that a definition, or is it just actually it happening? Because it looks like it's actually it happening. For batch in that, we have a batch, we give it to the model, we have outputs, we have loss dot backward, y, and then optimizer step, scheduler step, optimize 0 gradient, and then progress bar goes up by 1. Do I just run it? Would you look at that? Is that our progress bar from Taqaddum? That's pretty. And this is taking not so long. Oh wow, look at that, it's moving over them. The green thing. Tell me what's happening. You can see that the core of the training loop looks a lot like the one in the introduction. We didn't ask for any reporting. No, we didn't. So this loop will not tell us anything about how the model fares. We'll need to add an evaluation for that. Okay. All right. Now you're just wasting my time. The evaluation loop. As we did earlier, we will use the metric. A metric provided by the evaluate library. We've already seen metric.compute method. Yes, we have. All right. Okay. But metrics can actually accumulate batches for us as we go over the prediction loop with the method add batch. All right. Once we have accumulated all the batches, we can get final results with metric.compute. Okay, so here's how we would implement it inside the loop. All right, so these are normal. Hold up. Oh, that's a different loop. That's an evaluation loop. So we're now going over what? Model.eval, and then where's eval data loader coming from? Oh, we made that like somewhere at the top. So we're just going over the data, the evaluation data, and then same way we are going over the training data. We have outputs, and then logit and prediction, which we add to the add batch. That actually is similar to what we did last time. So my time was not wasted. Sorry, I would like to apologize. Okay, a bit more, and then we'll have something to look at. The results might be different because of the randomness. Got it. So cute. Okay, if preparation for sleep is done, yeah, machine learning gushes. If preparation for sleep is done, this little doggy and me. Hello, Doohoo. It is I, and that over here. Yes, SCL, a Doohoo, and a Yuk in the wild. I was just about to say walk into a bar, but I probably would not walk into a bar. Oh, that was funny. No. Let's compute that. Okay. But if it's a bar where I hit my face, then sure, I'll walk into that. Supercharge your training loop with HuggingFace accelerate. Oh, it did. All right. Then joke accomplished. our F1 score is higher and our accuracy is higher. Good for us. Okay. So it's mostly sleeping time. So I know Yuki was preparing for bed. So Doggy and I are saying goodnight to you. And I know Duhu is preparing for bed. So please do that. While I try to accelerate my training loop with PyTorch. Yep. I tried to make the sound of the video match my sound. Let me know if there are any issues. Because that whoosh in the beginning is like super high. It maxed out OBS and I made it a bit lower. Okay, no maxing out. Yay.
Supercharge.
Alright, let's supercharge our training. But this is all done. Like, we technically did it.
Charge your PyTorch training loop with HuggingFace Accelerate.
Okay.
There are multiple setups on which you can run your training. It could be
I actually want to report something. I bought these really adorable pillows that I've seen YouTubers use as a backrest, and now I'm using it and I'm like actually really happy about it. It has a face and 2 arms. I don't know if you guys have seen those pillows, but like I've seen people use it when they're reading or when they're using a laptop on their lap and all of that. So I got it yesterday and I'm really happy. There. Now let's do acceleration.
be on CPU, GPUs, TPUs, distributed on one machine with several devices, or even several machines, often called nodes, with multiple devices. On top of that, there are new tweaks to make your training faster or more efficient, like mixed precision and deep speed. Each of those setup, or training tweak, requires you to change the code of your training loop in one way or another, and to learn a new API. All those setups are handled by the trainer API, and there are also several third-party libraries that can help. The problem with those is that they can feel like a black box, and that it might not be easy to implement the tweak to the training loop you need. Accelerate has been designed specifically to let you retain full control over your training loop and be as non-intrusive as possible. With just 4 lines of code to add to your training loop, here shown as the example of the training loop video, Accelerate will handle all the setups and training tweaks mentioned on the first slide. It's only one API to learn and master instead of 10 different ones.
Okay.
More specifically, you have to import and instantiate an accelerator object that will handle all the necessary code for your specific setup. Then, you have to send it the most.
I, like, at the same time, love and don't like when they're like, this thing does everything for you. Like, yeah, but thank you, really. I'm lazy, but, you know.
Model, optimizer, and data loaders you're using in the prepare method. This is the main method to remember. Accelerate handles device placement, so you don't need to put your batch on the specific device you're using. Finally, you have to replace the loss.backward line by accelerate tor.backward loss. And that's all you need. Accelerate also handles distributed evaluation. You can still use a classic evaluation loop, such as the one we saw in the training loop video, in which case all processes will perform the full evaluation. To use a distributed evaluation, you just have to adapt your evaluation loop like this. Pass along the evaluation data loader to the accelerator.prepare method, like for training. Then you can dismiss the line that places the batch on the proper device, and just before passing your predictions and labels to your metric, use accelerator.gather to gather together the predictions and labels from each process. The distributed training script has to be launched several times on different processes, for instance, one per GPU you're using. You can use the PyTorch tools to do that if you're familiar with them, but Accelerate also provides an easy API to configure your setup and launch your training script. In a terminal, run accelerate config and answer the small questionnaire to generate a configuration file with all the relevant information. Then, you can just run accelerate launch, followed by the path to your training script. In a notebook, you can use the notebook launcher function to launch your training.
Okay. So the accelerate's job is to make multiple things that we're using come together. All right. So the training loop we defined earlier works fine with a single CPU or GPU, but using accelerate, HuggingFace's accelerate library, with just a few adjustments, we can enable distributed training on multiple GPUs or TPUs. Okay. All right. That is actually useful. Starting from the creation of the training and validation data loaders, here is what our manual training loop looks like. So where are we? This is the model. This is our optimizer. This is our making sure we're using CUDA, and then epoch, and then how many training steps we have, our learning rate scheduler, our taqaddum progress bar. I will flex my Arabic pronunciation at any chance I get, obviously. And then inside the loop, model.train, inside the loop, for each, I will say for each, forever. For each epoch in the range of number of epochs, and then for each batch in our data loader, for the batch being the things that we saw. We're looking at the output of the model given that batch with all the things. We have a loss, and then we say loss backward. I'm not sure why we are doing that, but that's how it should be done, so it shall be done. Am I going to look it up? No. Optimizer.step, and then learning rate goes up, and then optimizer being some, I think it's just like being zero gradient. I don't know. Is that from the word gradient? And then progress bar. Wait, I don't see us using the accelerate. You just made me review this without seeing accelerate, and now it's like, here is what we added for accelerate. I feel cheated. Okay. From accelerate import accelerator, we add that line, and then we instantiate it, and then we don't need to do the CUDA thing. We do train. Whoa, hold up. Train data loader, eval data loader, model optimizer by saying accelerator. Oh, dot prepare. Okay, so we're basically updating all of this using accelerator dot prepare, and then we don't even need to do the batch thing. That's and the loss backward thing. The only line is that. Quite interesting. Because we did the V2 device, and now we don't need the CUDA thing. All right. Should I update? Where are we? Because like the code starts all the way here, and I don't think, no, I don't have anything not in this setup, but let's see. First line is the first line to add is the important line, Second line instantiates the accelerator. Yes. We saw that right here. And then that will look at the environment and initialize the proper distributed setup. The HuggingFace Accelerate library handles the device placement for you, so you can remove lines that put the model on the device, or if you prefer, change them to use accelerator.device instead of device. Alright. Then the main bulk of the work is done in the line that sends data loader model optimizer to accelerator.sparse, that part. Okay. This will wrap those objects in the proper container to make sure your distributed training works as intended. Okay. The remaining changes to make are removing the line that puts the batch on the device. Again, if you want to keep it, use accelerator.device, replacing loss backward with accelerator.backward loss. I probably do that. I probably keep the device just to know it's happening. Right, little doggy? In order to benefit from the speed up offered by cloud TPUs, we recommend padding your samples to a fixed length. So yeah, that was a note elsewhere. Padding for TPU should be uniform overall, not by batch. GPU allows that, TPU doesn't. TPUs are I don't know, strict. If you'd like to copy and paste it to play around, here is the complete. Thank you. You're making me lazier than I should be, and I'm already plenty lazy. I'm gonna add a line where it says we're using accelerate. Why does that sound like a spell? There, okay. So we just run. We'll see how long it takes, because we know how long this took. 2 minutes 46 seconds. Might not see any difference because I'm not using multiple GPUs. Okay. So putting this in train.py script will make that script runnable on any kind of distributed setup. To try it out on a distributed setup, run this. I might do that. I actually have access to somewhere where there are 2 GPUs, and I might do that and compare the difference, which will prompt you to answer a few questions and dump your answers in a configuration file used by this command, which will launch the distributed training. If you want to try it in a notebook, okay, that's all. Wait, did I just finish this part? The full training? Why did that take, why was that faster than the trainer API? Whoa! We're going to do the quiz now, after I read this part. Fine-tuning check. That was fun. Yep, pretty fun. In the first 2 chapters, you learned about models and tokenizers. That was these chapters, yes. And now you know how to fine-tune them for your own data. Yes, but only text data. I wanna do more. To recap, in this chapter, we learned about datasets in the hub, learned how to load and pre-process datasets, including using dynamic padding and collators. Implemented our own fine-tuning evaluation of a method. Yes. Implemented a lower level training loop. That was fun. Used HuggingFace Accelerate to easily adapt the training loop so that it works with multiple GPUs or TPUs. Which one was your favorite part? and then wait for a few seconds and say, mine too. So that dog's name is Boots now. Let's do the quiz. And this is still running. And it's literally the exact, one more second added. Yeah, we didn't make any changes because our setup was the same. End of chapter quiz. Let's see what we learned in this chapter. The emotion dataset contains Twitter messages labeled with emotions. Alright, search it for the hub, read the dataset card, and hey, it's just called emotions dataset. Alright, I'll search that in the hub. Here's our hub. Oh, dataset, not models. Okay. Is it still there? That's the only one called emotions. I don't know if it's from, I'm not gonna use it, but wait, no. The one with like, I don't know, most likes. There, it should be that one, I'm guessing. Is it from Twitter? Are these memes? Or are these actual human emotions? Sorry, okay. Someone help me, where's the Twitter emotions dataset? Dogs. Speech. Do I just look for Twitter? Tweeta. No. Oh, tweet emotion. Okay. If it's not that, then mangeta. Let's see. Do we have emotions? Try sentiment using NLTK. So are we talking about the for this question? Because NLTK is like its own library, and I'm sure it has a list of sentiments, but right now the question is, there's a data set on the hub on HuggingFace. Like, it just wants me to learn how to use it. It's not me solving code. It's just me finding a data set. So I'm gonna there, we have something else. And if it's not that, then again, I'm in trouble. YAML. Huh? So nothing. Okay, I'm gonna wing it. I didn't find it. Didn't expect to find it. Yeah. Yeah, no clue as well. Let's try and wing it. Something tells me love is not an emotion. I don't think it's an emotion. Like, joy, confusion, and surprise are emotions, but yeah, okay. Apparently love is an emotion. Then joy is like